first seminar this week, and Andreas Prohl from Tübingen, and we speak about operator splitting method for stochastic incompressible Stokes equation. Please welcome.
Thank you very much. First of all, I would like to thank for the possibility to report on some recent results jointly with Erich Carelli from Tübingen and Erika Hausenblas. So this is a numerical talk. So the idea is that we have a simple problem, which is the stochastic incompressible Stokes equation. And since we have a simple problem in some sense, we want to have a very simple numerical algorithm to solve this problem. So starting from experiences in the context of deterministic Stokes equations, which will take maybe 10 or 15 minutes, which is part 2 here, I would like to step over to the stochastic context. So let me repeat again, we have a simple problem and we would like to have a very simple numerical algorithm for this in the context of numerics. So what do I mean by the problem which we are considering? So we have here the stochastic incompressible Stokes equations. We have a linear problem, and we have an L2 type of noise driving this problem. And we will come back to the role of stochastic of the noise of stochastic noise in the combination with simple numerical schemes in the main part of my talk. Okay, so we have some setup which is put together here, which allows for which I call here strong solutions. So this all is well understood, and I don't want to detail this too much from an analytical viewpoint. Again, as a numerical analyst, I would like to address the question which is posed right here. So we have a simple problem in some sense, a linear problem. So is it possible to use a simple numerical strategy to solve this problem accurately? And what I mean by the last word will be detailed below. So for instance, we have involved quantities like the velocity field and the pressure, and there's a rich body of literature in the deterministic setting how to discretize the deterministic problem properly, and because you have to simultaneously compute velocity field and pressure. Note that in analytical studies normally the pressure is deleted by some projections, which is not the case in actual computations. Okay, so as I promised, I would like to detail a little bit the very simple method that I would like to use to solve the non-stationary Stokes equations in the deterministic setting, so no noise. So I would like to detail the Chorin method and afterwards refer to computed quantities, which we will now detail in a second, as to Chorin iterates, as opposed to Euler iterates, which I will recall for you in a second. So Chorin's projection method goes back to the late 1960s and has the goal to simplify the computation of successive velocity and pressure iterates. So this is a time discretization scheme, no space discretization here so far. So what we need is a grid covering the time axis 0t, and let us now start on such a time axis. So let us start with the first step. So this is t0, which is actually 0, and here we go to the first time t1, and the difference between t0 and t1 is k, which is equidistant, so it's fixed. So what do I want to do at this time t1? The first part consists in computing something which I hope to be an approximation of a velocity field. We will go to this further in a second. And the second computes actually the pressure P in some sense. So the first step computes U tilde 1 by completely ignoring about the relevancy of the Lagrange multiplier. So the K is given here again, so the deterministic increment here. And basically we are solving here an elliptic problem for this, an elliptic problem here. And the output has zero boundary data, but is not incompressible anymore. So the second step is referred to as projection, which is the reason for the name. Basically, what is happening here is that we take this the computed guy U tilde 1 here, and maybe move it over to the right-hand side and make a Helmholtz decomposition. So we compute something which is solenoidal, and we get a gradient. So unfortunately, the computation UM, because it's an L2 projection, does not have the right boundary data anymore. So it's only that in normal direction, the computed U1 as opposed to U tilde 1 vanishes. So we have some tangential freedom, we have some tangential non-zero contributions. Let me recall our problem, which is the deterministic Stokes equation, goes together with homogeneous Dirichlet boundary data. So in the strategy of Jorin is first compute some gas U tilde. Please focus on this notation, because I will refer to on the next slide to U tilde. And afterwards we project and hope the best. So that's how the scheme works. So we easily understand that this can be easily solved numerically, for instance, but this is a little bit suspicious so far. So what we do is we apply the divergence operator to this equation. So by observing the second constraint, the first guy will drop out, will be 0. So then we have divergence of U tilde m, which unfortunately is not 0. And then we get a Laplace of Pm. So if I move this to the right-hand side, the contribution related to this one, what we get is the second line. So we get actually a Laplace problem for the pressure P1. So we are here sitting at time T1. So first we have U tilde 1. So then we compute P1, which is in H1 modulo R, which carries some boundary data. So we see that the Neumann derivative of the pressure has to vanish. So this is inherent to the scheme. So why this? I'm sorry. Why this? Because we consider again this equation on the boundary, go in normal direction. So use this identity here and use the fact that we have full Dirichlet boundary data for U tilde 1. So we end up with vanishing Neumann boundary conditions for the computation P1. But once we have U tilde 1 and P1, just thinking now in terms of algorithmic aspects, then we can compute easily from this equation U1, which is now in H, where H is the set of incompressible functions, which is given in the second line. So no zero boundary data anymore. We already talked about this situation. Okay, let me just recall, we have the first equation which goes here in u tilde, and u tilde is here as well. There is no u tilde. But now what we can do is combine these two equations in order to start an analysis and understand what is going on here. So let's replace the m here by m minus 1. So there is a cancellation if we add. So we get u tilde m minus u tilde m minus 1. So then we get this guy, and this goes from the past, comes from the past. What does it mean? We get the new iterate u tilde m minus the old one divided by by k. This is the difference quotient notation which we have here to remind you that this is a little bit related to evolutionary problem. The information of the pressure comes from the past. I discussed this already. And this equation with epsilon equals to k comes from the second equation. It's just the restatement of the problem. So the computation, please give me another 1 minute to discuss the algorithmic relevancy of Chorin's method. The computation is quite easy, simple. So we compute the velocity field, so then the pressure, and then an updated velocity field. Very easy, and can also be generalized to a Navier-Stokes setting. So all results which I show here in a deterministic setting can also be done for this nonlinear case as well. So, so there are some advantages which I don't want to detail too much here in where the letter B is written. So there are advantages from this. This algorithm has advantages if it comes to space discretization. Yeah, I don't have time to detail this here now, and we only think about Chorin's scheme as a time discretization scheme. But the question is, does such a scheme perform well? This is given with the letter C. How about the convergence properties of the scheme for strong solutions? So for instance, my main statement here in this second paragraph of my talk is Euler iterates are as good as Chorin iterates. So what I mean by this will be detailed in a second, under the assumption that solutions U are strong, for instance. But this goes together with a statement, Chorin iterates are much easier to compute compared to Euler iterates. Because Euler iterates have to simultaneously go together simultaneously with the computation of P, of the pressure, while this goes in one step after each other. So this is my main statement, which will be detailed on the next slides. Chorin iterates are as good as Euler iterates in the deterministic setting. We will see that this is not the case in the stochastic setting. So we see, first of all, that the U tilde m, let me just go back again. The U tilde m is computed from here, where the gradient of P is missing, is not divergence free, and satisfies, in fact, this this line here, which comes from the second line from above, on the above. So we have this is called, motivated from numerical setting, a pressure stabilization method or a quasi-compressibility method. So we are perturbing the incompressibility constraint. Also, we are requiring, we are asking the pressure to satisfy this constraint, which is not valid in the context of Stokes' equations. There is no constraint for the pressure on the boundary. Okay, I try to summarize things again. So iterates are not solenoidal, so not divergence free. So we have this quasi-compressibility constraint. We have a non-physical or a non-mathematical boundary condition for the pressure. And also because of the semi-implicit setting, what does this mean? This means that the pressure here comes in an explicit fashion because of the splitting character of the method. First U, then P. So this avoids an immediate discrete energy law. So one also has to think about this at some point. So the result which is known so far is that if we have a strong solution, so these are data informations here, then the Chorin scheme or the Chorin iterates, this is the bottom line, are as good as the Euler iterates. So which means that we will come to these weights in a second. If we compare the solution U with the Chorin iterate in L2, we get a first order, which is exactly what we expect for Euler and can also be proven. Here, for the gradient of U, we get a decay. So in fact, if you delete this one and put it over here, we get a square root of k, which is in some sense related to the fact that we have non-physical boundary data for the pressure. I will detail this in a second. So then, since we have non-physical boundary data for the pressure, we have to go to a norm which ignores, this is due to H10, which ignores boundary effects. So then we get optimal approximation behaviors for the pressure iterates, of pressure Chorin iterates. And if we go to the L2 norm, this one sees some so-called boundary layers, which I will detail on the next slide. And we have then reduction with respect to order. So all these results go together with a transient time in the sense of error estimates. So the bottom line is that Euler iterates are as good as Chorin iterates. And I would like to, in order to recall this for the later one, I would like to write this down again. Chorin iterates. So they solve dt u tilde m minus Laplace u tilde m plus nabla phi m minus 1 equals to fm divergence u tilde m minus k, which is the penalization, or the parameter here is 0, and d nu pm equal to 0 on boundary. So we have also the Euler iterates. And they are, I only would like to address the velocity here, which is, so there's a v, which means incompressible, So here the u tilde m are contained in h1 naught. Here I put the v for divergence free. So dt vm minus Laplace vm plus qm equals to fm, and divergence, okay, vm is equal to 0. So these are, I call them Euler iterates, and here I call them Chorin iterates. So they are of similar type, or the rates of convergence with respect to L2 norm here is the same. So what can be done further about the approximation of the pressure in the deterministic context? So in the deterministic context, this is one remark: the pressure has, of the original problem, has some good regularity properties. So the pressure has some good regularity properties, and then I can start with a numerical analysis. And I already mentioned the fact that because of the boundary condition which we have here, there is a boundary layer of size delta where the approximation behavior is quite bad. So I'm talking about the approximation behavior of the computed iterate Pm to the pressure Ptm. And things are going wrong here, where the delta is the distance of the boundary layer. And this can be qualified here, leading to the following result, basically. So this here says, basically, if you consider the L2 error in the interior, which I now marked there, then results become better. Yeah. So, and the delta, the ominous delta, which I wrote over there, is linked to the time discretization scale k, which is given in the second line. So we have here the time discretization scale k. So this here is approximately square root of k plus a logarithm. So many things have been understood in the deterministic context about the approximation behaviors of Chorin iterates. And we see that there is a recoupling of accuracy properties of the pressure to the approximation properties of the velocity field. So I would now like to turn on to step over to the context of stochastic Stokes and see what happens there. So I think this can now can go quite fast. So we have u tilde m here, which is h10 valued, and now we have the noise here, and the rest is the same. So we have a deterministic setting here, which marks the projection, and a strategy could be like this. So again, we can reformulate our scheme and interpret and write an effective equation for the u tilde m, which goes together again with a deterministic equation, which is the second one for the which violates the incompressibility constraint. And then we have non-physical Neumann boundary values. So the question is now, and I would like to show you results on the motivating computational results on the next slide. How does this splitting scheme perform in a stochastic setting? Okay, I will go back to this in a second. The green, which is obviously not so good to see, marks the Euler iterates now in a stochastic setting. Every time you see green, maybe you feel remembered that this is the solution of this problem here, which is Euler iterates, which has a which involves a simultaneous computation again of Vm and Qm for every m. So, and before I show you as promised the pictures, let me just recall that in a broader setup, which can be used right here, Guillaume and Millet analysis lead to square root of k for problems like that. So on the next slide, I will show you again the third time as promised an error plot. So I would like to show to you the solution UTM minus Euler iterate with respect to this evaluation. And I would like to show you the corresponding error for the Chorin iterates, stochastic Chorin iterates. So here we expect square root of k, and you will see that the computations show exactly this, or also better results. And Chorin iterates will show you a much worse rate of convergence here. So let us start. So Chorin is left, Euler is right. So Euler, we look first on the right picture, and we see the red straight line in this double logarithmic plot. And this red line gives order of convergence with respect to delta t, which is k, which is 3 over 4. 3 over 4. So what we see here for the Euler iterates, blue curve, is that if we are refining or making smaller the delta t, which is k, so then at a rate which is better than, so look at the blue curve, at a rate which is better than actually 3 over 4, not only 1 over 2, we get nice approximations. So let's now step over to the Chorin iterates And the straight line here is now not anymore, it does not correspond to 3/4 convergence rate, but to 1/4. And we see that the blue curve is approximately like this. So something has happened here. So the yeah?
What is the noise?
That's exactly the question. So we have here general L2 noise.
General space-time white noise?
Yeah, L2 noise, yeah.
Probably not space-time.
Well, I mean, is L2 the covariance of the noise, or is or does the noise live in L2?
The noise lives in L2.
But it's not space-time white
assumption that
noise.
it was trace class. That's what
Trace
we mean.
class.
Yeah, trace class, sorry. Yeah, I'm sorry, yeah.
But is it like just about trace class? I mean, so do you take the covariance that is k to the minus something which is just about summable?
No, it's we take some combination of I think 10 or so profiles, eigenvalues, for instance.
Oh, so it's really not.
It's finite in this sense. But it's L2 noise, and we will now see that it depends decisively for Chorin iterates and the quality of or approximation properties of Chorin iterates, whether it is divergence-free noise or general L2 noise.
Oh, so here the noise is not divergence-free.
Okay, so so these experiments motivate that in general, Chorin scheme, which is easy to compute, gives a reduction of convergence rates for general L2 noise. So the story which I explained to you before in the deterministic setting was that Chorin iterates are as good as Euler iterates. This is not the case here anymore.
But even in the deterministic case, it wouldn't be the case if you take the deterministic forcing, which is not divergence.
It is. In this case, so then everything is wonderful.
They're both the same order.
Yeah, yeah. So the only point is the role of the pressure, right? The approximation of the pressure, which is somehow Chorin iterates are hindered here by this constraint.
So in this assumption, and the middle assumption is that the noise here is divergence-free.
That's the main message of the whole talk. So a simple method, if you want to have a simple method, you also need a simple problem with respect to stochastics. So the result here is then that Euler iterates are, Chorin iterates, stochastic Chorin iterates are of the same quality as stochastic Chorin and Euler iterates are of the same quality in case the noise is reasonable, which means divergence free. I showed you a counterexample on the previous slides. So I would like to shortly discuss the 3 steps how to prove such a thing. And actually, the proof is very easy. And so I can maybe follow the slides here a little bit.
You can maybe take, if you want, the stick over there.
The stick,
Oh,
yeah.
in the case of Euler in your numerical experiment, the convergence rate was actually better than 1/2.
That's right. So it's not affected. Because also you consider again the projection, the projected form, right? And then you can use Millet and György. And so here you have to account for something extra.
So is it also going to be better than 1/2?
So in these plots here, so it seems that if, let's say, we have the complicated scenario, L2 noise, general L2 noise, then we get here a better rate of convergence, but maybe this is due to the actual computation. So our computation was, or our example was maybe not bad enough. So I think square root of k is what we can expect.
Okay, but here in the case of nice noise, you have better than.
This is bad noise.
Yeah, but I mean nice in the sense of smooth.
Yeah, okay. Yeah.
But whether it's divergence free or not doesn't matter at all because you project it out at every step anyway for Euler.
Okay.
So
Okay.
it's still kind of nice.
Okay.
Now the question is if you take your Shor and iterate with nice, smooth, divergence-free noise, then is it going to be better than square root of k, just like Euler is better than square root of k?
I would state it in a different sense. So first of all, what we observe here is that for general L2 noise, Shorins, iterates don't produce square root of k. So if we have nice noise, so then we now expect square root of k because of the next slide. Yeah.
Yeah, but you expect better than square root of k, just like here you had better than square root of k.
Yeah. Could be. Yeah.
So you didn't do the simulation. You didn't produce a
Okay. I did. This has been done on some slides later. I will show. So let me point out again. So the type of noise is relevant for the performance of the splitting Turing scheme.
So when you have, just to summarize, because there was maybe some confusion, that when your noise is divergence free, so that is the assumption B, then your estimates are the same as for Euler scheme of Georgi Millet.
Yeah.
The same square root.
The same square root. Yeah. So as I said, the proof is very easy, and I try to survey this a little bit. It's right here. So let us recall what are the error effects in this scheme if I put here a stochastic noise as well. So we have, first of all, time discretization effects. We have pressure stabilization effects. And we have time explicit usage of the pressure here. So we have three effects, A, B, C, which I now would like to discuss a little bit. So A is error due to time discretization. And this has been done last 9 by Gyongyi and Millet. So the implicit Euler, or the Euler method, I always refer to Euler as implicit Euler method, gives first and second energy laws. So which we obtain in a straightforward manner. Again, green means Euler iterates. So we have this result, and we see no pressure here whatsoever because we projected this away. There's no question like this. So now the main step comes here, and it's very easy to see actually that if we interpret this equation in L2, for instance, once we have detected about role of this one, so then we can multiply by nabla p m. Oh, I'm sorry, I have to go to here. By nabla q m. So this gives the guy on the right hand side. We have already under control this information here, which is in A2. This cancels, and the noise, which now comes in addition, is 0 because it's orthogonal to nabla q. A very easy observation. If you integrate by parts, you have divergence-free noise. This guy vanishes. That's I don't tell you more than just this today. So we have stability A1 and A2. We have control over the gradient of Qm, which means Euler. So we have stability and approximation behaviors. So the next step, I'm sorry, is the effect of pressure stabilization, which means the second, so the perturbation of the incompressibility constraint. So let me, so in order to detect this better later on, this is UTM minus WM. So now I'm interested in WM minus WM epsilon. And WM epsilon is almost the equation for U tilde M, apart from this guy. So this is used in an implicit fashion. And now let's try to prove an energy law. Again, as I said, it's very easy. So the first guy, M epsilon minus W M minus 1 epsilon. I hit this guy by WM. So then I use binomial formula. So 2a minus b, a is equal to a to the 2 minus b to the 2 plus a minus b. So therefore I can rewrite this in this fashion. In epsilon Wm minus 1 epsilon plus Wm epsilon minus Wm minus 1 epsilon to the 2. So then the next guy of interest is nabla Qm epsilon, comma W M epsilon. So, but then I use the second line. So I hit this guy by Qm epsilon. So Qm epsilon, I integrate by parts. So this is the same like minus Qm epsilon, zero boundary data for the Wm epsilon, divergence Qm epsilon, and this is the same like the epsilon, which is k, nabla Qm epsilon. So we see that there is an extra k, which is deteriorating if compared to, deteriorating if compared to the previous slide, the information with respect to the pressure. So there's an extra k or epsilon sitting on the left hand side after summation and making expectations. I'm sorry. So okay. So then the next term is W B. I'm sorry, B of Wm, and then we have nabla Wm, and we hit this by Wm epsilon again, but now we make a mistake, and Wm epsilon minus Wm minus 1 epsilon. So everything is very easy here. So if we now make make expectations, for instance, this guy vanishes because increments are these are. I'm sorry. Here we have an m minus 1. So the expectation here is 0. Here we first make Young's inequality, and this contribution goes to here. It's controlled by this one on the left-hand side. And this here will be controlled by isometry and properties of B. And this leads eventually to an energy law again, a discrete energy law, which, as I already said, has a bad dependence on epsilon, which is k. So we lose something. It seems we lose something. I call this first bound because on the end of the next slide I will produce the same, show the same quantity of interest for you again without the square root of epsilon. So in a similar flavor, and really not more complicated than this one here. So we can now make a perturbation analysis for this linear problem and end up with this result. So the only information which we ask for in the perturbation analysis is the information of the Euler iterates. So, but the Euler iterates on the last but one slide are controlled nicely for the pressure. So this, the control here leads then to C times K. So we get optimal rates for the in the context of perturbation analysis, which we are here, which we are in this item, which we need in this item. Right? Okay, but then we have information with respect to error. So we have a K here, sitting here, and sitting here. So at the end of this error analysis, rather than stability analysis, we can deduce the stability again. And this is then important for the last step, which I don't want to detail, which is the error due to semi-implicit use of the pressure. So the error, which is related to this one, and U tilde M, which is now the Turing iterate, the stochastic Turing iterate, has to be investigated in this step. And this relies on stability properties, in particular on stability properties of iterates of the Q, which is the pressure here. And I don't want to detail this. Again, simple analysis of the same height or level of complication leads to this result. So as a conclusion, we have for special noise, which is divergence free, we are able to do the step A3, which gives us control over the pressures for the Euler, so the Euler iterate pressures. So this required that the noise is divergence free, and then the related perturbation analyses lead then to the optimal result, and this proves this little theorem. So to have a conclusion, stability and perturbation analysis are involved, and it is crucial to control the pressure, and which is related, so Lagrange multiplier is related to the type of noise. This is my point here. And in this case, that the noise is divergence free, splitting schemes, so very simple schemes, are as good as more complicated Euler schemes. This is my message here. Computational studies. So the little arguments which I showed to you evidence or prove that if we have solenoidal noise, then approximation properties of the very simple Turing scheme are much better compared to the horror scenario which I gave to you first. So here are some plots. So we see here a red curve which is 0.5. So it's 1 over 2. Convergence rate is 1 over 2. So we see here in the computations the blue curve which is sitting here, which marks the strong approximation with rates observations. So it's of square root order as proven. And the Euler scheme is actually much better. Here, this is again 3 over 4. So here are some profiles. I mentioned of pressure iterates pathwise, and not only pressure iterates, but errors of pressures pathwise. So here are expectations of pressure errors at a certain time. This means very fine, very small k equal delta t, coarser delta t, and causes delta t in our computations. So what we see here is that we have this boundary layer structure, so that the errors concentrate here close to the boundary. This is a similar phenomenon to what I reported on in the deterministic setting, due to the fact that we have non-physical boundary conditions for the pressure. So they get more and more marked the bigger you choose the time step. And here we see maybe some related structures of boundary layers. Okay, and then just to complement the results, computational results, in the case of non-solenoidal noise, and draw you some pathwise pressure errors, we see that in this context, again, maybe the boundary layer structure is not so marked anymore. Again, you only see here Chorin iterates. And we have again we observe some boundary layer structures for the error of the pressure, which is more marked for expectations. Oh, that's all. Thank you very much for your attention.
Questions?
In the case where the noise is not divergence free, can you get that k to the -1/4 bound?
No. No. We tried, so far we are not able.
So there's no theoretical result about.
Yeah. So we have two questions. One is exactly your question. So we were not able to answer so far. And the second question is, how can we improve the standard Chorin scheme to do better and compensate for this defect, this deficiency? Maybe we can.
The other question is, do you have a theoretical explanation why Euler actually gives you an h to the 3/4 here or something like that?
No. So you're saying it could be related to the type of noise. So we are using smooth noise and which?
Well, you work in a setup those estimates where your noise is kind of appropriate. In the sense, if you get noise which takes everything in a better space, you actually get better solutions with respect to space variables. So it could have some effect on the rate of convergence, but something which has to be investigated.
Yeah. So personally, I conjecture that the problem simply was not as bad enough in this setting for Euler iterates to only approximate at a rate square root. So I think this is sharp in some sense. This is related to this is sharp, to my opinion. But maybe I'm wrong. Maybe I'm wrong. My question. So this is a numerical analysis talk. And I think most people here are analysts and stochastic analysts. Is the question, how good is the pressure? I mean, this is what it was about, right? How good is the pressure for the stochastic Stokes? If once we get better results in this direction, we can also construct maybe better schemes.
So I mean, as I said, I think that in the case of at least non-divergence free noise, your pressure will have to be an eta process, and then so if you can get a good estimate when you're looking in the wrong space for the pressure. So, and then you have when you have two parts of your pressure, which is one is boundary variation, and another is this second part. Then that is the way you can get a good estimate.
Could be, yeah.
That is the point here. That one really in the non-divergence free case of noise. So, no more questions? Thank you very much.
Thank you.